In this video, we will solve a question on constraint optimization. The question is, suppose consumer's utility function is given as u is equal to x plus 2 times y plus 1. X and y are the two goods and u denotes the utility that is derived from the consumption of these two goods. Price of good X is $4, price of good Y is $6, and income of the consumer is $130. We are supposed to use the Lagrangian method to answer the following questions. That is, first write the Lagrangian function. Second question tells us to find out the optimal levels of good X and good Y. Third part tells us to find out the second order condition, whether the second order condition for maximum is satisfied or not. Fourth question tells us to find out the total utility at the optimal level of x and y. Fifth part tells us to find out the marginal rate of substitution, and sixth part tells us to find out the marginal utility of money, and last part tells us to derive the demand function for good x. Okay, this video will get a lengthy. Okay, so bear with me and you will learn it perfectly. Okay, so the first thing is what we are being told. We have a maximization problem. That means consumer wants to maximize the utility u is equal to, and let me rewrite this utility function. We have x plus 2 into y plus 1. If I rewrite it in this fashion, multiplying, first we have x into y, then we write plus x into 1 is x, plus simple multiplication I am doing here. Then we have 2 into y is 2y, plus 2 into 1 is 2. Okay, so I can rewrite the given utility function as xy plus x plus 2y plus 2. Okay, this is our utility function. Now the endeavor of the consumer is to maximize this utility subject to the constraint that is he is facing. So what is the constraint that this consumer is facing? That is, the constraint is that price of good x times units of good x plus price of good y times units of good y should be equal to the total income of the consumer, and let's denote it by I. Okay, since in this question it is being denoted by I. Okay, so consumer wants to maximize this utility subject to this constraint. Okay, so such that what is price of good x? That is being given us as 4. So in place of px I will write 4x plus price of good y is 6, so I will write 6y is equal to total income of the consumer is $130. So the endeavor of the consumer, of a rational consumer, is to maximize the utility, that is u is this very stuff, subject to this budget constraint. Now how will the consumer do this? We need to answer that very thing. So first part tells us to write the Lagrangian function. How do we write Lagrangian function? What we do, we write, and let me show it here. So let me write it here. First part is, so how do we form the Lagrangian function? There are steps. First step is we set this this constant equal to 0. Okay, so that means 4x plus 6y minus 130 is equal to 0. Or let me do it another way. So let's transpose all the terms to RHS. That means it will become 130 minus 4x minus 6y. Okay, first step is to set this constant equal to 0. Second step is to multiply this constant by lambda. Let's denote it by L, sorry, by lambda, that is this symbol. 130 minus 4x minus 6y is equal to lambda times 0. Okay, we multiply both sides by 0. Now then we have the third step. Third step is to form the Lagrangian function, and let us denote it by f. So Lagrangian function is the aggregate of the given utility function and the resulting constraint that we constructed by first setting this constraint equal to 0 and multiplying it both sides by lambda. Okay, so what will be our Lagrangian function? That will be equal to this objective function plus this resulting constraint. So we have xy plus x plus 2y plus 2. Okay, this constraint, sorry, this utility function plus to this we add the result constraint that we formed here, that is 130 minus 4x minus 6y. Okay, this is the part for, sorry, this is the solution for first part here. Okay, let me rub this now. Next question is that we need to find out the optimal levels of good x and y. To find out the optimal bundle or optimal levels of good x and y, what will we do? We partially differentiate this Lagrange's function, with respect to x, y, and lambda, and set them equal to 0 simultaneously. Okay, then solve them. So let me yeah. Okay, let me repeat it. My English is out of nowhere. So to find out the optimal values of both x and y and of lambda, we partially differentiate the this Lagrange's function with respect to x, y, and lambda, and set them equal to 0 simultaneously and solve them. Okay, that means, and let me write it here, let us denote f subscript x, that s f subscript x means the partial derivative of this Lagrange's function with respect to x. Okay, so derivative of x is 1, so we are left with y, plus derivative of x here will be 1, so we will be left with only 1. And since no x is involved in these terms, its derivative will be 0 because we are taking the partials here. Now here we have x, so derivative of x is here 1, so we are left with minus 4, and minus 4 will be multiplied with lambda, so we will get minus 4 lambda, and we set it equal to 0. Okay, and if I rewrite it in this fashion, that is 4 y plus 1 is equal to 4 lambda if I transpose this lambda to RHS. Okay, symmetrically, let's take the partial derivative with respect to y. That means partially differentiating this Lagrange's function with respect to y, derivative of y will be 1, so we will be left with x, plus derivative of x will be 0 because we are taking the partials with respect to y. Here derivative of y is 1, so we are left with 2. And here we have y in the last term, derivative of y is 1, so we are left with minus 6. So minus 6 into lambda is minus 6 lambda, and we set it equal to 0, which implies x plus 2 is equal to 6 lambda. Okay, then we take the partial with respect to lambda. So since no lambda is involved in the first 4 terms, derivative of lambda in the last term is 1, so we are left with 130 minus 4x minus 6y, and we also set it equal to 0. Let this be equation first, equation second, and this be equation third. Then what will we do? We divide equation first by equation second. Okay, let me write it here, equation 1 upon equation second, which will be equal to, which implies, so equation 1 is y plus 1 divided by equation second is x plus 2. So we are dividing LHS with LHS, and then we will divide RHS with RHS, 6 lambda. Okay, now let me rewrite it because I have n number of questions to answer here. So let me simplify it. So it will become we have y plus 1 upon x plus 2 is equal to 4 lambda upon 6 lambda. Lambda gets cancelled. 4 we can write 2 2s are 4, 2 3s are 6 when we simplify this. That means 3y plus 3 is equal to 2x plus 4, which implies 3y will be equal to 2x. If I transpose this, it will get subtracted, so 4 minus 3 will be 1, which implies y will be equal to 2x plus 1 divided by 3. That means when we simplify it, we will get, which implies y is equal to 2x plus 1 upon 3. Okay, now what will we do? We plug the value of y into the budget constraint. Okay, what I have done here, when I simplified this, I got the value of y as this stuff. Now I plug this value of this value of y into this equation. Let us say this is equation a. I could also put it into equation third, but for the sake of simplicity I am taking it into equation a. When I plug the value of y is equal to this stuff into equation first, what will I get? So we have 4x plus 6. The value of y is this 2x plus 1. 2x plus 1 upon 3, which is equal to 130. So here 3 ones are 3 twos are 6. It will become 4x plus 2 into 2 is 4x plus 2 is equal to 130. So these are the like terms. I can add them. So it becomes 8x is equal to, transposing this, it will get subtracted. It becomes 128. That means dividing both sides by 8. So 8x divided by 8. 128 divided by 8. 8 gets cancelled. That means x will be equal to 8 ones are 8. Oh, now the kaba, so 4, it becomes 48. 8 48. So we will get 16 as the value of x. That means when we plug y is equal to 2x plus 1 upon 3 into this budget constraint, what we are getting the value of x, we are getting 16. Okay, and let me write it here. 4x plus 6, the value of y is 2x plus 1 upon 3 is equal to 130. When we solve this, as I have done here, we got the value of x is equal to 16. This is the optimal value of good x. Now to find out the optimal value of good y, we simply plug the optimal value of good x into this equation. Okay, so here we put the value of x. So our y will be equal to, y is equal to 2, the optimal value of x, which is 16, plus 1 upon 3, which will give us divided by 3 go. So we will get the value of y is equal to 11. And let me write it here. Y is equal to 11. So we got the optimal values of good x and y. So we are done with the first two questions, and let's take them tick a tick. Okay, now let me draw this our curve here. Okay, third part tells us to find out the second order condition. Okay, this was actually the second order condition for maximum. Second order condition for maximum was that we form this Lagrangian function and differentiate partially with respect to good x, y and lambda and set them equal to 0 simultaneously to get the values of x and y. Okay, so but this is only the necessary condition. Sufficient condition for maximum we need to check. That is the third part. So third part is to find out the sufficient condition for maximum. Okay, now second order condition, we also call that second order condition. Second order condition can be expressed in terms of a bordered hessian. Okay, so we need to construct a bordered hessian matrix here. By bordered hessian matrix, what exactly is meant by, we take the partials, that means second order derivatives of this Lagrangian function. Okay, and sorry, so these are the first order derivatives. We take the second order derivatives of the Lagrangian function, and let me first construct it. So bordered hessian is being given by, h is being given by, we need to find out the determinant of this bordered hessian matrix, and let me write it here and I will explain it. Let you know, so we write here f of x, f of y, f of xx, f of xy, f of yx, and f of yy. Okay, so then what we do, we write 0 here, and here we write c subscript x, and here c subscript y, Here we write C subscript x and C subscript y. So what exactly is the bordered Hessian matrix? Bordered Hessian matrix is formed by taking the second order direct and cross partials of the given Lagrangian function. Okay, and then we border this matrix, this green matrix, with the first derivatives of the you know constraint function. And let me write it here. Let me show it what exactly is meant by f subscript xx. Fxx means the partial derivative of the second order partial derivative of the Lagrangian function with respect to x. So this is the first derivative. Second derivative means we differentiate the first derivative with respect to x again. So f subscript x is y plus 1 minus 4 lambda. We take fxx means partially differentiating it with respect to x, since no x is involved here. So fxx is equal to 0. Similarly, fxy fxy means taking the derivative of this f subscript x with respect to y. Here we have y derivative of y will be 1. Okay, we are taking second order derivatives. So let me explain it here. F subscript x means the first derivative. F subscript xx means the second derivative with respect to x. Okay, and fxy means the derivative of this function with respect to y this time. Okay, now we have fyx means partially differentiating this function with respect to x, since no, so we have x, since the derivative of x is here 1, so we will write it here as 1. Now we have fyy means partially differentiating this function with respect to y again. No y is involved, its derivative is 0. So what is exactly the bordered Hessian matrix? It is simply a plane Hessian. When I am saying this, fxx, fxy, fyx, and fyy, this is called the plane Hessian. Okay, when this plane Hessian matrix is bordered by the first derivatives of the what I call this megumashti, we call it constraint function, and we write 0 here at the principal diagonal. Then we form the what we call this bordered Hessian matrix. And let me uh, write here C subscript x. C subscript x, let us say this function, if I write it here, we have 4x plus 6y minus 130. Okay, let us say it is a function. We write C is this function. Okay, constraint. C subscript x means the partial derivative of this function with respect to x, so we will be left with 4. C subscript y means the partial derivative of this constraint function with respect to y, which is 6 here. Okay, so what will be our bordered Hessian matrix now? So our bordered Hessian matrix will be equal to, so we have 0 on the principal diagonal, 0 on the principal diagonal, then we have cx cy, cx is 4, cy is 6. Here we have fxx, we got it as, and first we have cx cy again, 4 and 6, 4 and 6. Then we have fxx, we got it as 0, and fxy is 1, fyx is 1, and fyy is 0. This is our bordered Hessian matrix. Now we need to take the determinant of this bordered Hessian matrix. Okay, so what we say, this is bordered, it is a plane Hessian matrix. We say when the plane Hessian matrix is bordered by the partial derivatives of the constraint function, we call it bordered Hessian matrix. Okay, so what we need to do now, we need to take the derivative, sorry, we need to take the determinant of this borrowed Hessian matrix. So if we, and let's write it here H2. I will explain why I am writing here H2, or let me explain it here. Since the plane Hessian matrix is of order 2 by 2, we also call it second bordered principal minor. Okay, when the second bordered principal minor is bordered by the first derivatives of constraint function, we say this is a bordered Hessian matrix. Okay, we call this H2. H2 is equal to this H. Okay, I don't need to, you know, make it more complex. So H is actually H2 here. Okay, H2, and the derivative of this H is, sorry, I am stuck with that derivative in my mind. The determinant of this matrix is, how do we find out the determinant? Let me write it here. So determinant of H2 will be equal to, first we write this term, this 0. Okay, there we mentally delete this row and this column and take the determinant of the remaining element. So 0 into 0 is 0, minus 1 into 1 is 1. Then we write minus and write the second element, which is 4. When we write the second element, we mentally delete this row and this column in which this element appears, and take the determinant of the remaining elements, that is 4, 6, 1, 0. Okay, so 4 zeros are 0, minus 6 ones are 6. Then we write plus and write this term. Now we multiply this term. We mentally delete the row and the column in which this term appears and take determinant of the remaining element. So 4 ones are 4, minus 6 zeros are 0. Okay, when we take the determinant here, you can see we will get here 0 into this step is 0, minus 4 into minus 6 is plus 24, 6 4s are 24, so we will get here 48. So determinant of this H came out to be plus 48, and let me rub this out. H is equal to H2, which comes out to be 48. The determinant of this matrix is second bordered Hessian matrix is greater than 0 when the determinant of this whole matrix is greater than 0. What we say, so bordered Hessian is positive. When it is greater than 0, here it is positive, and we call this bordered Hessian is positive definite. Okay, so the determinant of this came out to be 48, which is positive. We say this bordered Hessian is bordered Hessian is positive definite. Positive definite. And this positive definite Hessian satisfies the second order condition for relative minimum. And let me write it here. And this positive, I am really sorry for this mistake. When this is greater than 0, we say the bordered Hessian is negative definite. Okay, negative definite. Let me repeat it again. If the determinant of this bordered Hessian comes out to be positive, we say bordered Hessian is negative definite, and negative definite, okay, Hessian satisfies the sufficient condition for relative minimum, sorry, relative maximum. Okay, I don't need to repeat it again. If the determinant of this bordered Hessian matrix comes out to be positive, we say it is negative definite, and negative definite Hessian satisfies the sufficient condition for relative maximum. So we are done with the third also. Now we need to find out the total utility. Okay, total utility will be equal to, so this is our utility function. U is equal to x plus 2 and y plus 1. We need to find out the total utility at the optimal value. So optimal value is 16 and 16 and 11. So plug the values here. So we have 16 plus 1, 16 plus 2, and 16 plus 2, y plus 1 means 11 plus 1. So this is 18 into 12. So 18 into 12, 2 8s are 16, 18 into 12, 2 8s are 16, 2 1s are 2, 2 go 3, 1 8s are 8, 1 1s are 1, now the ka. I hope I am doing this calculation right. So we got here 216. So total utility will be equal to 216. Now comes the fifth part to find out the marginal rate of substitution. MRS is simply equal to the marginal utility of good x upon marginal utility of good y, which is simply the partial derivative of utility function with respect to good x, that is the marginal utility of good x upon marginal utility of good y, means the partial derivative of utility function with respect to y. Okay, so if we differentiate partially this utility function with respect to x, so what will we get? We will get derivative of x is 1, so we are left with y plus derivative of x is 1 upon derivative of this function with respect to y will be x plus derivative of y is here 2. So this is our MRS here, y plus 1 upon x minus 2, and it is always negative. Okay, marginal rate of substitution. To find out the absolute value, you can also find out by plugging the value of 16 and 11 in place of x and y. So okay, we are done with the fifth part also. Now sixth part tells us to find out the marginal utility of money. Marginal utility of money is actually the value of lambda. Okay, so the value of lambda is the marginal utility of money. And what exactly is meant by this lambda? It's simply, first we need to calculate the value of lambda till there figure out what is meant by, then we can interpret it. Okay, so how do we find the value of lambda? We got the value of x and y here. To find out the value of lambda, we plug the values of x and y either in equation first or in equation second. Okay, let us plug in equation first, which implies y. So what is the value of y? Y is 11 plus 1 is equal to 4 into lambda. 4 into lambda, solving. So 11 plus 1 is 12 is equal to 4 lambda. Dividing both sides by 4, we will get the value of lambda comes out to be 3. So we got the marginal utility of money equal to 3. The value of lambda is 3, which is the marginal utility of money. Now how do we interpret this? The value of lambda simply tells us how will the utility change if there is 1 unit change in the constant of the constraint function. Let me repeat it again. The lambda, we also call it the shadow price. It simply tells us how will total utility change when there is 1 unit change in the constant of the constraint function. Okay, so गुस्से में इधर उधर निकल जाता है. Let me repeat it third time. By lambda is equal to 3, it simply, if we want to interpret it, it simply tells us how will total utility change when there is change in the constant of the constraint. And what is the constant of the constraint? It is actually M, that is money. How will total utility change when the money changes by 1 unit? What we call the marginal utility of money. Okay, okay, we are done with this also. माफ करना, गुस्से में इधर उधर निकल जाता है. Now the seventh question tells us to find out the demand function for good x. For that very thing, I need to rub this. We have to rub this out now to solve for last part. So for this, we write the, so we want to maximize the utility function u is equal to xy plus x plus 2y plus 2 subject to the constraint that is 4x plus 6. No, we don't need this to find out the demand function for good x. Okay, so what is the demand function, what will be the budget constraint, that is price of good x times units of good x plus price of good y times units of good y should be equal to the income of the consumer. Okay, now consumer wants to maximize this utility function subject to this budget constraint, and we need to find out the demand function for good x. How do we find out? Simply we use the tangency condition here. Okay, that will be suffice here. So we equate MRS with the ratio of the prices, price of x upon price of y. Graphically it simply means, um, given this budget constraint, okay, uh, consumer wants to, this is the indifference curve. Okay, so this condition tells us that marginal rate of substitution should be equal to the ratio of the prices. Px upon py means the slope of budget line, and this mrs means the slope of indifference curve. Okay, so at the tangency point, let us say this is x, this is y, at the point of tangency MRS, that means slope of indifference curve and slope of budget line are equal. Okay, so MRS is simply marginal utility of good x upon marginal utility of good y. It should be equal to the price ratio, price of x upon price of good y, which implies mux is the partial derivative of utility function with respect to good x, and marginal utility of good y means the derivative of the utility function with respect to good y. It should be equal to the price ratio, price of x upon price of y. Okay, now let me rub this out, which implies dux upon dx means the derivative of this function with respect to x. So derivative of x is 1, so we are left with y plus derivative of x is 1, so y plus 1 should, du upon dy means partial differentiation of this function with respect to y. Derivative of y is 1, so we are left with x plus derivative of y is here 1, so we are left with 2. Price of x upon price of y. Question and code. Let us solve this now. So we have py into y plus py is equal to px into x plus twice px. Okay, let's solve it for y. That means we need to write py into y is equal to transposing these terms. So we have px into x plus twice px. Transpose this here, we have minus py. That gives us y will be equal to px into x plus twice px minus py, dividing both sides by py here, so we will get py here. Okay, now we need to plug out this value of y into the budget constraint here. So we have price of x into x plus price of y into the value of y is this stuff, that is price of x into x plus twice price of x minus price of y divided by, am I writing it correctly, price of x into x plus twice price of x. Okay, then we have price of y. Then this will get cancelled, so we will be left with, and it should be equal to I, that is the income. Solving it, so price of x into x plus price of x into x, that is twice price of x into x. Then we have plus twice price of x minus price of y is equal to 1. No, 1 is not, it is income here. We need to solve for x this function, so we will get yapariga sources. So we have twice price of x into x is equal to I. Transposing these terms, it will become minus twice px plus py. Okay, now dividing both sides by twice px, we will get x is equal to I minus twice price of x plus price of y, okay, divided by twice px. Okay, this is the demand function for good x. How did we arrive at this situation, simple thing, we have to maximize this utility subject to this general budget constraint. First we need to find out the tangency condition, that is first order condition for maximum. That means MRS should be equal to the price of x upon price y. MRS is simply the slope of the indifference curve. Input price ratio is the price, sorry, this is the price ratio of good x and y. Price ratio simply denotes the slope of budget line, the point where the slope of indifference curve and slope of budget line is equal to 0. We have the optimal point. So solving this, MRS is simply the ratio of the marginal utilities of good x and y. And what is marginal utility of good x? That is simply the partial derivative of utility function with respect to x upon partial derivative of utility function with respect to y denotes the mu y. We equate it with the price ratio. So solving this, du upon dx is y plus 1 is du upon dy is x plus 2. We equate it with price of x upon price of y. Okay, solving for y. Okay, when we solved it for y, we got the value of y as this stuff. Then we plugged the value of y back into the budget constraint here to find out the demand function for good x. I hope I make myself clear in this video. Thank you.